There we go. That are there to help you get to this resource. Thank you. Yep. All right, there we go. Yeah. Sweet. Awesome. So back to that. So at the hub, yeah, you're going to see these FPGAs, these GPUs, CPUs. We have IC and AC922s configured in this cluster and a bunch of memory. So that leads to some actual realistic things that you would see when you're going to get access to Bare Hub. You're going to get bare metal. You're going to get CI/CD. You're going to get analysis, containers, virtual machines, operating systems galore, whatever you need. And that really just starts enabling all of these awesome things that the community and the industry needs. So hub components really actually are made up of 3 different things. We have people, hardware, and then the platforms and architectures that bridge those 2 things. The first thing we're going to talk about is people, because that's really why this exists, is for people out there to start using it. You get developers, you get system engineers and admins. Academia and industry is going to be there. So basically everybody here that wants to use the Power Hub, they can. You're also getting the hub providers. So that's including us, University of Oregon with their Exascale Computing Center, Vantosh over with Toshan, I believe his name is. And you're also getting Raptor Computing. And then you're getting the SIG, so the providers. And then because it is also a public work group, anybody. This. Next thing up is hardware. So we have 6 AC922 Witherspoon systems. So we're talking about 16 cores in each one. So you're looking at 32 cores, 128 threads, like cache up to 3.8. These also has a terabyte of memory, so large quantities, so not just simple things. 4 NVIDIA Teslas on each system. So these are the Volta architecture, 32 gigabytes of HBM2 itself, and the interconnect link also, which I really like to emphasize. That gets you access to OMI, meaning that you can actually put those GPUs on the system. You can, if you get access to one of these bare metal systems, you can throw a terabyte of memory at a GPU. That alone is a huge increase over what we can actually see in the industry anywhere else. And then you're getting 40 and 25 gigabit network interfaces at the moment. That's what we could buy. We didn't have networking running into this. We haven't got any better donations. That's what we have. We're kind of scrambling to get more, but that's the name of the game, right, for everybody. Oh, and these are also, as I said, on these GPUs, these are SXM2, meaning they're socketed to the motherboard. They're shorter distance. You're not running across PCI at this point at their limitation. And then we also have 6 IC 922s, the Mihawk systems, 12 and 24 systems. We got a mixture of these here, but most of these machines, 5 of them are running 256 gigs of DDR4, but we have one with 512 that's on reserve. These are the ones with the FPGAs. So these are where we really start getting into, this is a collection of hardware. And then on top of that, we have 25 gigabit interfaces on those, and we have T4s for also more, tensor flow working, workflows. And we have those on hand because we haven't yet figured out how we're going to use them, where we want to use them, etc. Up next, we have platforms and architectures, some of the stuff that actually makes this stuff work. First thing is we have bare metal. Yes, we will actually be loaning out these systems that you see here, and these are actually all rack. I love my cube. Velcro. Data center cannot go anywhere without Velcro. So yeah, these systems will be on loan. At the moment, we only have one, but the AC 922s, which you see on the right there, are all technically in OpenStack right now, which is one of the other platforms we're going to be talking about. We will be able to pull those out if demand allows. Same with the IC 922s potentially. A actual holistic list of what we have here, just for your specs and what we have. That should show up. There it is. We have, there's each one. Yeah. So if you need specs, again, these are slides are going to be uploaded to the Google Drive, so anybody can actually grab them. That leads me to our 2 other platforms, which effectively, are OpenStack and OpenShift. I heard some talks about OpenShift and it being relatively new, so that's why we're here to actually announce that as well. OpenStack and OpenShift are very similar. They are both open source. They are a form of managed virtualization and infrastructure, and both very complex. Like I said earlier, I've been learning a lot in a year. They expand on really heavily used but more basic technologies, VMs and containers. They can both heavily be automated, and just for the sake of it, they both have a Red Hat implementation if you want paid support. So the first thing we're going to talk about is OpenStack. OpenStack basically started from Rackspace and NASA wanting a highly reconfigurable VM compute environment a long time ago, actually. Some of the core components that we're currently using of OpenStack are Nova, Neutron, which provide you your VMs and your networking in between them, even software-defined networking and physical networking interlinks as well. Getting Keystone, which is giving you access to effectively basically creating tenancies so that you can manage projects by yourself, in a sense. No one actually be seeing everybody else's stuff. We got block storage and Cinder, image management. So if you need a specific VM image to start from scratch, we have that as well. A dashboard if you want to start looking at your specs, and telemetry via celeometer to actually show, okay, are my systems up and down? How are they performing? And then a command line client if you're feeling so tech savvy. Some future hopeful components that we're hoping to get into as we're a few versions behind in OpenStack are resource reservation. So those GPUs that we talked about, you'll be able to reserve those. The FPGAs as well via OpenShift we'll talk about as well. Object storage in Swift for enabling larger container management as well. Bare metal provisioning, so OpenStack will potentially be able to just automatically on the fly provision somebody a bare metal system. Accelerator lifecycle management via those GPUs that we are so coveting now. Orchestration via heat so that all of this can be just press a button and go. Monitoring, so we have some better insight into when things go up and down. And then if OpenShift is too much for you, we're also going to try to see if we can get just basic simple containers up and down soon. So enough on OpenStack, we're going to shift over to OpenShift. Basically, in a nutshell, it's a distribution of Kubernetes, but just with a lot of overhead on it. It's dev and ops focused in a sense. They make it, I guess in a sense, a point to classify that. It has developer views and it has administrative views. Developer views for working with applications, administrative views for actually like the system engineers. They're saying, okay, where are all my resources? What's my compute load? That kind of thing. And then on top of that, it's working with CRIO-based containers. They are more closer to the Linux kernel, and that you get higher security. And with version 4, which is what we're running here in on the hub is running with Podman instead of Docker. So you're getting something newer. And then on top of that, if you really just want to take it over to the cloud, you can. OpenShift is supported on many cloud providers, bare metal, and they classify it also as platform agnostic, which is kind of leading into how we made this work in a sense. But really, we want to do it on the hub because we want power systems. So we're going to do a little build out of what the hub actually looks like architecture-wise. Users are going to be able to access all of this just through the internet. I mean, if you want to run your own private VPN connections into some of your stuff, you can. If you just want to run over SSH via a public internet connection, you can. All of that hardware is going to be accessible. So again, we're going to have bare metal systems at the IC 922s and AC 922s. And again, all of these are going to be slotted in a sense. We're going to give you time slots. So no one can actually just hog 6 GPUs at a time. Again, we're integrated with OSL's OpenStack, so you get all of those handy features as far as project management, image management, all of these things that allow you to spin up a VM and burn it down in a matter of minutes. Those OpenStack instances also will actually give you those V100s via PCI pass-through. So if you want those into VMs, you can have 2 if you want in a VM. And that's where OpenShift actually also lives technically, is within OpenStack. We've actually hybridized it into OpenStack. We have virtual master nodes actually managing the entire platform. We also have workers, in a sense, where you can spin up containers in those virtual machines. And then on top of that, we also have 3 IC 922s dedicated to actually just running containers also. The reason for this is the OpenCAPI FPGAs. Those FPGAs are readily made available via those containers. So you don't actually get root access to the system. You get to actually run an action image. You can say, well, I'm checking out an actual FPGA in a container, but you don't get root access to the hardware. It's much more secure and still allows the developers that are running to work with these FPGAs a chance to work with them. Oh, well, that's what I just said. Just like the bare metal, those FPGAs will also be time slotted. We also have a handily provided by CQLS x86 system currently for running GPU GUI enabled, so basically a desktop image for actually building those images for those action images on OpenShift. We will have the ability to actually allow you to build images with them available as well, not just your own software. So the hub also exists for, there's a lot of people on campus that want to use it, and research is the biggest thing that sometimes we need to want to start using this, because research is one of the biggest things going on right now. Actually, over at CQLS, at the Hatfield Marine Science Center, which is out in Newport in Oregon, we did a little experiment. Chris loves this part of the talk because he basically did it all. He used his own AC 922s, so not the actual hub, but the same AC 922s with V100s, train a model used to identify 173 different types of plankton by using a little piece of physics that we know called as the thin hole experiment. They shined a laser through a small hole and cast a shadow using it to make plankton look bigger. So then they could actually take those images, segment them, and identify. So they dragged 2 AK cameras behind this ship on a boat. And then basically you get 10 gigabytes of video per minute, leading to 7 terabytes in a typical 12-hour session. 10 days at sea will give you 70 terabytes of raw video data. Then you have to actually use that data to work with.
That's the lowest.
But the lowest. So again, it's going towards making research happen. So the OpenPOWER HUB allows groups to test V100s and T4 GPUs. But then, okay, these systems use a lot of electricity. I mean, granted, price per performance, they are still pretty good, but they use a lot of electricity. The boat generator can't actually run them. They said you can't bring those systems on this boat. So they had to use something a little different. We actually got a donation, worked with Western Digital to use one of these Ultra Star Edge ruggedized edge servers. They basically give you like this military box that you could drop this thing from out this window and it wouldn't break. But because that edge server is not the same as a power server, you do all your training and all of your actual testing on the AC 922s and the IC 922s, and then take that model out and implement it on that Western Digital box. Yeah. Oh, there it goes. There's the animations. So during the entire spectrum there, you guys can reach here, but basically they captured 64 million images out at sea because of the training and testing provided by these power systems. This would not have been able to be done on basically any other system without a lot more time. So, and I'd also like to mention that students also participated in this. They helped write the algorithms. They helped train the AI, undergrads actually specifically. So on the right here, it's really hard to read, but that is a segmented image of just, Chris, can you tell us how many different types of plankton are in that?
No.
No? Oh, okay. But there's
We have so we can only do a small percentage, but it allowed us to see semi-real time from the testing. So we were able to take the stuff from above, put it out at sea, and ultimately give semi-real time so we knew we needed to change positions of the ocean and how that affected. This is a very idea, very complex, and that's why we basically show how
so then they're basically the very last question becomes, well, this is great. How do we use it? Where do I sign up? Well, you actually just head on over to the OpenPOWER Foundation Hub page. Effectively, it's you go to the top of the page, click that Hub button. It's literally right there. It's super simple. It's going to give you the 4 options. You got OSU, you got University of Oregon, Vantosh, and Raptor. I don't actually know the status of where Schmidt, where's U of O at? Can people sign up?
I believe they can sign up over here, like application.
Okay.
Then they have to sign up for the University of Oregon.
Okay, gotcha. And that's exactly kind of similar to what is happening with us. Basically, you fill out the form. It looks similar to this. It's going to tell you what kind of resources are they available there, and then it's going to ask you to fill out a form. And basically, we're asking for your name, what you're doing, basically what your project's about, how it's open source, and then what kind of resources you want. You want Power 9, Power 8, you want FPGAs, you want GPUs, what do you want? You want bare metal? Okay, we'll work with you. That's why this form exists. So if you actually want to go to that form, here's a QR code, making this handy for you guys. I mean, everybody saw people taking pictures, and QR codes take you directly to that page if you want. Got one coming. And actually, just in case anybody wanted any of the links in this presentation, we have that as well. So if there's a targetable somewhere back there, I don't know. We have the talking about when we talked about Jenkins, that's on the left there. The OpenPOWER Foundation Hub is in the middle, and if you need the those handy dandy tools that we were talking about with all of the compilation and build tools and thousands of pieces of software that we use to actually build the software for our researchers, that's on the right as well. And lastly, some acknowledgements, just to say thank you to all of these people. Everybody, Lance Albertson and Pam over at OSL, Ken and Chris over at CQLS, and all of the undergrad students that make this possible. Barath, who also basically is a mastermind at actually getting IoT stuff to work. Everybody over at OpenPOWER, Bob, big shout out to him, Stan, big shout out to Fabrice. I hope he's getting better. He broke his leg apparently recently. Bruno, Toshan, and then over at Red Hat, Colin Suggs and Jose Perez are resource reps. And then all of the software and actual one, I put the trusty number 2 Phillips in there too, because I do work with hardware. I get to rack this stuff. And on day 2 of my employment, when Chris said go rack, you know, like $1.5 million worth of equipment. I was like, you trust me that much on day 2? Okay. But that's all I have, guys. This is the Open Power Hub, and we're ready and willing to accept those requests and for everybody to start getting developing on Open Power.
Thank you.
Any questions?
Another video with AC922s, not many people know it. Go to a sporting event with a stadium. It's highly likely there will be a bunch of AC922s in the video.
Mhm.
They're tremendously good at moving a lot of data. And HDTV and sports broadcasting. Just a silly little piece.
And the GPUs need to be able to stream it.
The hub will have the power center. If how this be pretty possible. Really, you want to understand about this, what they want to do.
Exactly. Thank you.
Thank you.